We ranked them. Fastest growing was exponential in this whole thing, so this is rank number 1. But these 3 are exponential, so let's put a little exponential there. The bigger the base, the faster it grows. The biggest base is 2. E is 2.71, so it came in second. 2 is obviously 2, so that's third place. After that are the powers. Thank you for the externship reply. I'll get back to that in a minute. And then x to the 10th, fourth place, and then add the powers of x. You know, the higher the power, the faster it grows. So 4, and then 5, 6. Log is the slowest. It's the inverse of exponentials that are the fastest. Nick and Jake, you do have to pause for a second there. Now, next page is where I use it. Remember that we did end behavior not that long ago? It was, I don't know, horizontal asymptote type. That's what it says right here, horizontal asymptotes. We actually would talk about the limit as x goes to infinity is as you get really big values of x, the horizontal asymptote had 3 different options. It was, if it was top heavy, there was no horizontal asymptote. If it was bottom heavy, it was 0. And if it was the same power top and bottom, it was the ratio. But this one is a none because it's top heavy. That is, it grows faster on top. So what you end up with is a really big number on top over a smaller number on here. So it's top heavy, higher power. Higher power on top, top heavy. So this is x squared, I don't care, over x. I don't care. That's top heavy. There is no horizontal asymptote. What it means for the limit is as x gets bigger, it just gets bigger and bigger and bigger and bigger and bigger and bigger. Which is, if x gets bigger, it goes to infinity. Not 8, but infinity. Okay. That is the value of that limit. So on to the next one. It says the limit as x goes to, we're going to evaluate at infinite limits just like we did horizontal asymptotes. As x goes to infinity for this one, these guys are the same power. Do you remember the horizontal asymptote would have been like 1/3? Thanks, guys. So quiet and unassuming, but you're mad, aren't you? But the horizontal asymptote was y equals 1/3. That's the value of the limit because we're just putting in really big values of x. Oopsie, I can write this. So what we look at is the ratio of those lead coefficients is the value of the limit. What we weren't telling you is that the horizontal asymptote that we were getting before, that's actually what we call the end behavior. This is limits to infinity, 1/3. We call these end behaviors at extreme values of x. Okay, so limits to infinity talk about the end behaviors, and I mean 2 extreme ends. So first one was infinity because it was top heavy, got bigger, 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 bigger. Next one had same degree top and bottom, so it's 1/3. If you go out the horizontal asymptote, the graph levels off at 1/3. This next one, the limit as x goes to infinity on the last one, it's bottom heavy. And remember in horizontal asymptotes, it'd be like, oh yeah, y equals 0. Totally bottom heavy. That's the value of the limit. As x gets real big, you get 0 is the value of that limit. Okay, bottom of this. Guys, put those away, please, please, because you're going to ask me about this, and I'll say, I don't know. So this one says find both limits, left and right. It means who's winning. This is the race business. As x gets really big in natural log of x, picture natural log of x. We're going to put our graphs off here. So here's ln x, dirty dozen graph. Boom. Oops, there it is. Okay, there's ln x. 3 to the x is an exponential function. It's the inverse of that, so it's got to goes up like this. As x gets really big in each of these, we're going out this way and this way. They both keep going up to infinity, but they're not going to infinity like the height is getting higher and higher for both. The 3 to the x just gets there faster. That's the idea of getting growing faster. Like there is definitely a faster ascension on the 3 to the x than there is ln of x. So what that means for our values of these two, if I go limit as x goes to positive infinity, of ln of x. What it's kind of like is like infinity over infinity if you put it in directly. But the bottom one wins by so much more. It's bottom heavy, you get 0. What about negative infinity, though? Okay. What it looks like is infinity over infinity, but not like the same infinities. Like they're getting there at different rates. Negative infinity is kind of this is a funny one. The limit as x goes to negative infinity, this one's a little different. So I'm going to show you the graph here and see what you think. Not 3 to x, silly, it's 3 to the x. Okay, so 3 to the power of x. Okay. If I put in negative infinity, check out, if you go to negative infinity with natural log of x, it's not even there. If you go to negative infinity with 3 to the x, it's 0. So this one's a little weird. 3 to the x is you go way left. Do you understand that if I put in, I'm going to do orange here or something like that. But I'm talking about in each function, you go way as far as you can to the left on 3 to the x. Natural log of x, you can't even go to negative infinity. I will look at this one with you on Demomo because it'll be of interest. Check out this graph. So if I do ln x, bingo, over 3 to the x. Oh yeah, you got this. Zoom it out. The crazy thing is, look at that. It ends up going, as you go towards negative infinity, you can't put those kinds of x's in there. But there is something about it that's interesting. You can go towards 0. There is a domain issue that we're going to tackle a little bit later with limits. Sometimes this limit doesn't apply because the domain is restricted. And there's more to this story than we're going to get to. But the biggest one is, usually we just talk about limit as x goes to, we talk about the end behavior. We're saying, like, what's it do on each end? And as x goes to infinity that way, the top one was slower than the bottom one. If it's bottom heavy, you go to 0. The other direction, this domain is restricted, and we'll talk about that later. So this one ended up being a little harder to do. The last one, though, was really nice. The limit as x goes to infinity in this graph, totally bottom heavy, higher degree on the bottom, faster growing on the bottom, so it's going to be 0. And that's where I'm going to leave it. If you can tell whether, if it's bottom heavy it goes to 0, top heavy it goes to infinity. If it's the same rate of growth top and bottom, it's the ratio of the lead coefficients. So, oops, I went up too far. Those are limits to infinity. Now you get to play. Ready for some playtime? On Monday, we're going to talk about this thing called derivatives. So if you look down here, look at the word derivative pops up here. Total calculus coming your way on Monday. And it's limits. Look at this limit right here. We do derivatives entirely with limits. Isn't that cool? Get excited. How long were you going to say that? Okay, that one. That's derivatives. You're going to see it on Monday. You guys were not telling me? Could you not see the last one either?
No.
You guys, that's not cool because I recorded that. Let's do it again. So now we have to do it all over again.